Okay, so everyone, we start recording now. Okay, so hello everyone. It's a great pleasure to have Shubham here today presenting at our Vision seminar. So Shubham is currently a research scientist at Facebook AI Research located in Pittsburgh, and he's going to become an assistant professor in Carnegie Mellon University next year. So in the past few years, Shubham has done a lot of amazing and really interesting work in 3D vision. So one of his work was recognized by the CVPR Best Student Paper Award in 2015. And a lot of other his work has inspired like many follow-up works from various groups in the world. So just to name a few, we all know that lots of recent work have been trying to make the graphics rendering pipeline differentiable, right? And for instance, like the volumetric rendering work from Andreas Geiger and the volumetric rendering technique used in NERF. But actually, Shubham has did very similar thing already in 2017 in his CVPR oral paper. And one of the reasons I remember this is because that year CVPR was hosted in Hawaii, and I spent most of my time in the beach. And Shubham's talk was one of the few ones that I have attended. Okay, is Antonio here? Okay, he's not. Okay, great. Okay, and another thing is, recently we saw a lot of things on Twitter called 3D photography, right? Where people try to synthesize novel view from single image. And a lot of those techniques are based on a representation called maybe layered depth image. And this was originally introduced in graphics, but Shubham was the first one to bring it into the novel view synthesis context. And since then, vision community has do a lot of things with this thing. Okay, so as you can see, Shubham has done a lot of really cool stuff, and let's see what he's going to tell us today. Okay, so Shubham, we are very happy to have you here. It's all yours now.
Yeah, thanks a lot for the introduction. It's great to be virtually here. In fact, I was there in person a couple of years back. So this talk, I've tried to only talk of the stuff that's sort of new since then. But as a result, a lot of the slides were made at like 3 a.m. yesterday. So forgive if some things are not polished yet. And before I start, feel free to stop me at any point. In Zoom, I don't think I'll be able to see you raise your hand or something. So just speak up if you have any questions at any point in between. And yeah, I think just interrupt if anything is unclear or if you have any questions. So today I want to talk about, as the title says, self-supervised reconstruction and interaction. And at a glance, you might think these are two very different things. One is reconstruction, which is something about getting the 3D aspects of the world, and interaction is sort of about affecting the world. But over the talk, I hope to convince you that they're very closely related in that one is just about representing the world and then subsequently using that sort of a representation to do something meaningful in it. And sort of as I was making the slides, I kind of realized that a good subtitle for the talk is Learning with Newton in the Loop, where you can call supervised learning or learning from annotation as learning with human in the loop, where you get annotations from them. And a lot of what I'll talk about today tries to sort of do away with that by instead using principles from physics and geometry. And so sort of just cheekily learning with Newton in the loop. So yeah, before I start, I want to maybe take a couple of steps back and just note that for all of us who are doing AI or are in some subfield of AI, one of the grand goals has always been to build these sort of general purpose robots, right? So for example, here's the robot shown from the movie WALL-E. And we want to have these kind of intelligent agents that can do something meaningful across different scenarios. For example, hopefully I can have a robot such as this, which cleans my kitchen and living room, maybe makes me lunch or coffee or something like that. Or alternately, hopefully the same robot, if there isn't coffee at my home, can go to the restaurant near my house and go fetch coffee for me. And even looking at these very mundane daily life examples, we realize that for this particular agent to accomplish these kind of tasks, it really needs to understand the world at a very fundamental level. It needs to understand where people are, needs to understand where it can move around, understand how things will change, how people around the agent will walk, and so on. And so sort of towards this more or less grand goal of building intelligent agents that can meaningfully interact in the world, I just want to take a stock of where we are and how is it that we can sort of eventually get there, eventually build these agents. And well, any such agent will in some sense need to have two basic capabilities, right? And One is that of perception. That is, such an agent should be able to understand what it is that it's seeing. And the second capability is that of interaction. That is, this agent should then be able to accomplish certain goals or manipulate the world to achieve certain ends. And if we look at both of these individually, the tasks of perception or the field of perception and the field of interaction, these have actually been two great success stories across the decades. If we look at sort of perception or interaction on its own. For example, we have these amazing systems that can look at an image and classify what they're seeing, or classify, or sort of even go ahead and label the pixels of what they're seeing. For example, here are some results from ImageNet where, given this image, we could easily recognize this as a mite or a container ship and so on. And in parallel, over the decades, we've also made a remarkable amount of progress in building robots that can interact. For example, can do very dexterous manipulation tasks and are actually very, very useful these days in industrial settings. For example, in assembling cars or picking things off from conveyor belts and placing them in certain bins and automated packing and so on. So if we look at both progress in perception and interaction separately, we'll realize that we have made great amount of strides. But unfortunately, the things have not quite come together. We don't quite have robots that work in the real world yet. And I'd say that's because when we are looking at perception, we have so far primarily just focused on naming and labeling pixels. We have built systems that tackle perception for perception's sake by sort of recognizing images and pixels. And in contrast, the approaches we have looked at for interaction typically work only in controlled environments where in some sense the problem of perception has been abstracted away because these environments are controlled to be in a setting where we already know sort of the underlying state of the system. And so what I'd argue is that to get towards these more general purpose robots that can function in diverse settings, as a computer vision person, what I'd argue is we need to look at perception that is more directly useful for the kind of interactions that we want to do. And one way of looking at the techniques we have developed in the interaction literature is that we have learned how to go to actions given some sort of world model. So given an understanding of how the world is and how the world works, we have developed many techniques over the decades that can let us leverage these sort of world models to get to desired actions. And so in this context, sort of the role of perception is then to go from some sort of sensor input to build some sort of world models that can then be subsequently used for interaction. And sort of in this talk today, I'm going to roughly focus on how it is that we can go from these sort of sensor inputs to build some sort of world models that can then subsequently be used for interaction. And sort of at a high level, what we hope that these world models should capture is describe to us how the world is and how will the world change as a result of my actions. For example, if I pull this block away, the tower that is standing will fall down. And sort of one of the main questions in this quest to go from sensor input to world models is, how is it that we can acquire supervision for this? So we would, of course, want this sort of a prediction to work in novel scenarios that we have seen for the first time. We would want to be able to infer world models when we, let's say, visit a new house. So we clearly need some form of learning that relies on previous data. But the question is, what enables this learning? How can we derive supervised signal to go from these sensor inputs to some sort of world models? And there's been one very, very successful paradigm for learning that we have used across many tasks in the computer vision community, which has been to learn from many annotations. So for example, we can look at this task of image classification that I discussed earlier. And when we want to classify whether an image is a container ship or a leopard or so on, we can collect these millions of examples that for each image or each sensor input have the corresponding output annotated by a human. And we can use that as supervisory signal to learn the prediction function. And this has, of course, also worked for slightly richer tasks, such as instance segmentation using similarly large data sets, such as Microsoft Cocoa. But unfortunately, we want to use this paradigm for this task of predicting world models. This becomes a bit problematic because, figuring out annotation for what is the underlying world model given a particular image is extremely challenging. And I'd argue that getting such annotation is extremely costly and often impossible if we want certain details, such as, let's say, the mass of an object. And sort of in parallel, this is also not ecologically plausible. This is not how we humans learn. We humans just go around and interact with the world and learn to predict these, sort of learn an understanding of the world through our interactions. We are not given supervision by our parents that for this particular object, this was the specific mass, this was its shape, and so on. So there must be a slightly better way that we can learn to go from our observations to some sort of mental models of the world without relying on these tedious manual annotations. And the way I want to talk about is learning by prediction consistency. So what I mean by that is, given our visual inputs or sensor inputs, our goal is to predict some sort of mental model of the world. And because it's sort of a mental model of the world, it needs to have some predictive capabilities that are consistent with the laws of physics. So given a predicted model and a knowledge of, let's say, the laws of physics and laws of geometry, we could induce certain predictions from this model. This model can make certain sort of verifiable hypotheses or verifiable predictions, which we can match against sensor observations. And this can allow us to learn even without using supervision for what the true world models are. And so sort of the picture that I'm showing here at a very high level tries to learn a prediction function that predicts some sort of world models that are just consistent with available observations when viewed through the lens of physics or viewed through the lens of geometry. And what I want to cover in my talk today are a few instantiations of just this idea. So I'll sort of cover a few projects that instantiate just this idea of learning by prediction consistency for a few different tasks, sort of learning single view 3D prediction, or sort of understanding physical predictions from video, and lastly, learning some sort of forward models that are more directly useful for interacting with the world. And sort of to begin with, I want to focus on the single view 3D prediction task. And before I go into the method, I want to again motivate why it is that we need to go beyond 2D reasoning, why it is that we need some sort of a 3D representation of the world. So if I'm seeing this particular image, then the current recognition systems that we have will give us very accurate representations of this image in the form of these labels associated to instances or to pixels. That they'll identify that there's a couch on the left, identify the pixels that are associated with it, and so on for all of the other objects that are in the scene. But this representation itself is not very actionable. It's not very meaningful on its own. What it ignores is that this particular image is actually sort of a window to the underlying 3D world behind it. That this image is just something that a particular robot is observing from a specific perspective, and it's just sort of a canvas that points to the underlying physical reality that is behind it. And if this robot needs to go around and interact with the scene, or go around and clean the scene, or go and sit on the chair, it really needs to understand this physical reality behind the image as opposed to just the labeling of the pixels in the image. So, you know, if as an alternative, all we could understand of the image were these colored pixel groups that we saw earlier, then just that representation is essentially like having a painting, which is not really sufficient to be able to interact with the world. And so we really need some notion of the underlying physical reality given this image, that sort of given an image such as this one, we need methods that can understand what's really behind this particular image. And so just as one possible representation of the spatial structure, what we have been sort of, one possible approach to infer the spatial structure underlying an image that we've been following is that we want to be able to infer the 3D structure for all the objects in the scene, and then given this representation, compose a 3D scene. So what it may look like is we can infer the 3D structure of the chair, place it at the appropriate location, and similarly for the couch and the sort of the pillows, and place them on the couch, and similarly for the chairs, tables, cups, etc., and so on. And I'll not really talk about the composition part, or how do we compose a scene given all the objects, but what I want to focus on is how do we acquire the capability of inferring 3D for all kinds of objects that we might see, you know, which is a very diverse set. For example, even in this scene, things like lamps, bowls, and the sculpture, etc. So how is it that we can acquire the capability to predict 3D for any particular object that we see? So more concretely, the goal here is, given a single image of an object, such as this one, we want to be able to predict its 3D shape and corresponding camera pose, and sort of perhaps optionally texture. And here I'm just showing the sample result that one of our recent works gets on this particular image, and also maybe on some other images for these animals, for example. And again, before I go into details, I want to place this in context of a lot of prior work that has looked at this task of single view 3D inference. And in fact, the problem of single view 3D inference actually traces back to the very first computer vision PhD thesis ever written, which incidentally was at MIT by Larry Roberts, where given an input image, we wanted to figure out whether the blocks are pyramids or cuboids and where they are. So this was more framed as a 3D detection task where we a priori knew the shapes of the objects, but just wanted to find them in an image. And this actually culminated in very impressive demos, such as the one you see on the right, or more complicated template shapes, such as the ones you see on the left. And sort of this same approach of finding known shapes in an image is what continued over many, many years towards more complex shapes, such as the cabinets on the right or the razor on the left. But all of these approaches initially focused on identifying the known 3D shape in an image, whereas not really predicting the shape for a new object that they're seeing. And sort of that, to some extent, changed with the advent of deep learning and the availability of a lot of synthetic data, where the common approach then became to have an input image and learn a prediction function to infer some sort of a 3D representation. But across all of these approaches, the way learning would work is we would require annotations for the ground truth 3D associated with each training image. So all of the approaches that I'm showing above actually required synthetic training data for learning, and that doesn't generalize very well to real images, and the learned systems are not easily transferable to real images. And so to maybe do away with the requirement of 3D supervision, some approaches then looked at using multi-view supervision instead. So for example, given one input image, we could predict some sort of a 3D structure and say that it should be consistent with a novel view of the same object. And so instead of requiring ground truth 3D, we would require multi-view data for learning. But unfortunately, this is also slightly constrained because it's not very easy to get multi-view data even for a lot of object categories. For example, if you're thinking of birds, the bird will just fly away before you move around and capture the same bird from a different perspective. So, while reducing supervision to requiring multi-views is helpful, it doesn't enable large-scale learning, which is what we want to do when we want to reconstruct all kinds of object categories. So the form of training data that we want to be able to use are these image collections. That is, we have many, many images, but only a single view per instance. And for each instance, though, we assume some approximate mask segmentation as additional labels that are available to us. But using this form of data as supervisory signal can allow us to really learn very scalable systems that can learn 3D across many hundreds or thousands of object categories, hopefully. But the question is, so again, we want to be able to learn some sort of a prediction system that, given an input image of an object, can predict the underlying 3D structure, but only has this one view as supervisory signal, right? So the question is, how do we learn from this? And one possible solution is we can say that the predicted 3D should just be self-consistent. That is, whatever 3D we predict, it should be consistent with the input image from which it was predicted. And that is certainly a useful signal, but unfortunately, that's not sufficient by itself. And just to highlight this, here's sort of an example from Sinha and Adelson's seminal paper, where we are seeing the projection of some 3D structure on a plane. And this 3D structure could be something like a cuboid, or it could be something far more arbitrary. So there are essentially infinite possible 3D structures that can explain a single view, and all of these are sort of self-consistent with the 2D projection that you're seeing here. So we need some additional way to be able to distinguish these many degenerate solutions apart. So to be able to learn from these image collections, we can enforce geometric self-consistency, but that is not sufficient by itself because there are many possible solutions for the 3D structure that can explain a particular view. So in addition, what we might need to enforce is some notion of category level parsimony, that the shapes across a category do not vary arbitrarily. And so in sort of a recent paper that we put out on arXiv a couple of weeks back, we were operationalizing these ideas, and given an input image, we predict what we call an implicit mesh representation using this sort of an image collection as supervisory signal. So we have many images of birds, but for each image, for each instance, we only have a single view And importantly, we don't have any key point or post supervision, which several prior works assumed. And we just only have an approximate foreground segmentation mask. And we want to be able to learn 3D inference using this sort of data. Though in addition, we also relied on a single template shape per category. So across all birds, we have one template shape that guides us in learning the shape space, and sort of I'll describe that how in a bit. So before I go on, just to clarify what this implicit mesh representation is, and maybe to contrast it with an explicit mesh representation. So typically when we represent a mesh, we represent it as the locations of a fixed set of vertices. So we fix a topology such as a sphere, and we parameterize the sphere by, let's say, 600 vertices. So the representation of a mesh is this 1800 dimensional vector, which specifies the location for each of the vertices. And so, for example, we can pick a particular vertex and predict its corresponding location and so on for all the vertices, and this gives us a resulting mesh such as the bear shown here. In contrast, an implicit representation doesn't parameterize the location of specific vertices, but it's parameterized by sort of an arbitrary function that maps an arbitrary point on the original topology, such as the sphere, to a corresponding target coordinate. So it's a much more smoother and continuous representation compared to an explicit mesh representation. That given an arbitrary point, there's a function that maps it to a corresponding 3D location. So this is sort of the representation that we use in this work, except we specialize it to operate at a category level as opposed to an instance level. And sort of what I mean by that is across a category such as horses, we have different 3D shapes, such as this horse here or the other horse shown here. And we want an implicit shape space that can capture these different shapes in a category. So instead of having different implicit functions that correspond to different instances, we instead sort of parameterize it as being a latent variable conditioned implicit function. And this is actually very similar to this AtlasNet paper, if you're familiar with it, that each shape is represented by this latent variable, and then given any particular point on the sphere, condition on the latent variable, we'll get the shape of the appropriate horse. Except what we additionally do is factorize this implicit shape space to have a category level mean shape and only an instance level deformation. That is, across all instances, there's a common mean shape, and then the differences specific to the instance are only in deformations from that mean shape to the particular instance shape. And so having this factorization allows us to, where this mean shape we actually initialize by the template that I talked of earlier, but essentially having this factorization allows us to enforce category level consistency, because now across all instances in a category, we enforce that there's a common mean shape or the common phi bar that is shared across the implicit representations across all shapes. So given this sort of an implicit representation that can parameterize the shape space of a category, what we want to learn is prediction of this, we want to be able to learn the shape space as well as be able to predict the corresponding shapes for images in a category. So sort of more concretely, given an input image, what we want to be able to predict is the corresponding camera, that is, where is it that we are viewing this particular object from, and also what's its corresponding shape. And sort of just as I described earlier, for each category, we have this template shape, which can get deformed based on the predicted latent variable, and then projected back to the image coordinates using the predicted camera. Where sort of all of these functions, phi bar and delta, are actually things that are being learned on the fly with respect to the objectives that I'll describe. So given a particular image, we predict the camera and the corresponding deformation parameters, which allow us to transform a predicted 3D shape onto the image frame. And then we just say that this rendered 3D shape should match the foreground mask that we have available for this particular image. And in addition, what we also do is make per pixel predictions for what spherical coordinate is being rendered at that pixel. So for each pixel U, we predict what point on the sphere gets deformed and projected back onto this particular pixel. And the way that helps is it provides us an additional regularization to learn better 3D inference. So concretely, for each pixel, we have a prediction of what spherical coordinate predicts to that. And we say that this particular predicted coordinate, when mapped to the mean shape or when deformed and projected back, should basically come back to the location that it started from. And this prediction C is being made only using sort of very local evidence. So you can think of it as implicitly encouraging, pixels along the eye that look similar to predict similar spherical coordinates. So this cycle consistency loss just implicitly encourages semantic consistency, that similar points on the sphere map to semantically similar regions or regions that have similar appearance. And this sort of allows us to learn good poses without explicitly requiring key point supervision. And this was actually based on sort of a previous paper we had called canonical surface mapping, and I'd sort of encourage you to look into that for some more details. But just a combination of these two losses, where we enforce that the predicted shape should explain the foreground, and that the per pixel predictions should be cycle consistent, allows us to learn 3D inference using just these image collections. Whereas in addition, we also extend the variable Z to not just capture the shape, but also capture the texture that gets overlaid on the mesh. And I'm skipping some of the details there, but we can just do this by extending the loss to also take into account the color values at the foreground pixels. And then sort of what this framework allows us to do is, given a new image, make 3D inference, such as infer the 3D shape for this new image that we're seeing for the first time, and also overlay the predicted texture on it and maybe visualize it from novel views. And we see that both the shape and the texture that we predict is actually quite meaningful. And we do this across many categories because this approach is really scalable. It only requires approximate foreground master supervision to be able to make this sort of prediction. And it can even handle some sort of an articulation, such as the head of the horse bending down. And in the paper, we show results on about 30 object categories, because it's extremely easy to apply this approach to a new category. All we need is approximate segmentations for a few hundred instances in that category, and just one 3D template shape downloaded from the web. And this allows us to get sort of meaningful reconstructions across many, many object categories. And we also evaluate this sort of both directly and indirectly. So, given these two different images, the way we are reconstructing them is actually by deforming the same sphere, right? So there's a common sphere which, through the implicit function and a corresponding latent variable, gets deformed and projected back onto this image. So because they're being deformed through a common sphere, we can infer correspondences between these two different images by figuring out which point on the sphere gets projected to which pixel. So for example, this coloring here highlights that same points on the sphere get projected onto this location. So given a query pixel on the image on the left, we can find a corresponding pixel on the image on the right by finding which pixel had the closest point on the sphere project back at that location. And this allows us to transfer key points from one image onto the other and provides us a way of evaluating this. One other way that we also evaluate it is by annotating some semantic key points on the template shape. So just for testing, we annotate certain points on the template, that this particular 3D point is beak, this particular 3D point is tail, and so on. And we measure whether, when our 3D shape is reprojected onto the image, do those key points land at the locations where we expected them to. And we evaluate our reconstructions indirectly using the key point transfer and reprojection accuracies. And maybe I'll skip over some of the details, but yes, I think I just want to highlight that in the top row, the first approach, the dense equivariance approach, is an approach that does not use any 3D structure at all. And the two approaches in the middle, the CSM and ACSM, are approaches that do not allow shape variation. They use some 3D structure, but do not allow the shapes across different instances to vary. Whereas our approach, which allows predicting which allows a per instance deformation, gives us much more expressive power and is more accurate across both these metrics. And we also evaluated our approach on this 3D intersection over union metric on a different data set, where we could only compare it to previous approaches that used more supervision in the form of key points. And we observed that our results are actually quite competitive to the previous approaches as well. But unfortunately, there weren't any prior work which could get 3D reconstruction using just the amount of supervision that we were using in this work. But sort of, yeah, just going back to some more results. As I said, the approach we have actually works remarkably well across a diverse set of categories. So on the left, I'm showing the input image that we are seeing for the first time. Sort of the second row is a predicted shape viewed from the predicted viewpoint, and then it's textured, and then we see the predicted textured shape from a random novel viewpoint. And we see that the shapes are actually quite meaningful. We can sometimes capture articulation. For example, the head of the bear is a bit bent down, whereas the head of the camel is a bit bent up. And similarly works across different categories. One thing I'd note though is we are not very good at explaining very precise articulations. So while the head bending down is typically accurate, the location of the legs is not very accurate. And to some extent, that's because we only use approximate foreground mass as supervisory signal. And those are often not precise enough to give us very detailed leg estimates. And here are just some more results showing the predictions rotated from 360-degree views. And we again see that both the texture and shape are actually quite meaningful, though not perfect given the limited amount of supervision that we are using. And yeah, just some more results across different categories, like planes, birds, and hippos. Yeah, so now would be a good time if anyone has questions on this part of the work before I move on. I'll maybe pause for a few seconds if someone has any questions. If not, okay, I might then continue. So at a very high level, what I talked about so far was just this sort of a system that given an image could learn to predict some sort of a 3D model of what's underlying that image. And what we saw was to be able to learn this 3D model, we didn't need ground truth supervision for the 3D models. Instead, we could just say that this model, when viewed through the lens of geometry or viewed through the lens of Euclid's optics, should give us some sort of predictions. That is, how should the image look when rendered from a particular view? And we could just check whether that is consistent with respect to what we know. And in addition, some priors such that the shapes across a category don't vary arbitrarily could allow us to learn. So
Shubham, actually, this is David Bao. Sorry, I do have a question, and yes. I'm not going to be able to stay for your whole talk, but I wanted to get it in before I lost you. So when you're developing these very impressive methods, so you're showing some results on natural photographs. I'm just curious about your development process as you're trying to get your methods to work. Do you as you're developing these methods, do you work a lot with synthetic images as well to test your methods and get them to work first, or do you just work directly with natural images and get them to work in that domain?
Yeah, no, that's all great. So I think this specific work that I talked about was actually the culmination of maybe 3-4 papers before it down the line. So for this particular one, we were already well familiar with sort of the data, etc. So this we more or less tried in the real world cases, but the initial few papers were done in very, very toy settings. And in fact, not even 3D settings, but just more 2D settings where there's a square and you're observing a 1D image of it. And so first, a lot of the methods were debugged in this very toy setting. And over the years, then we became confident that these things actually do work. And
cool.
Yeah,
thanks.
more recently, it's more directly on the relevant data, but that wasn't always the case to begin with. Does that answer the question? Okay, cool. Yeah, I'm happy to take more if there are any more questions. Okay, if not, I guess moving on, and we'll maybe get some more time for questions at the end again. Yeah, so one view of what I just showed you so far was, given an image, we could predict some sort of 3D models that are consistent with the laws of geometry, as well as some priors that we have about how the world works. And as I alluded to earlier, this framework is applicable beyond just 3D reasoning. So, instead of just following Euclid's laws of geometry, we could also follow Newton's laws of physics and predict some sort of physical 3D models that have some physical priors and are consistent with certain, let's say, Newtonian laws. And the as an example of this, I want to just talk about this project where we were trying to basically understand interaction videos. So given a video such as, actually given many videos such as this one, where in all of them, it's actually, I think, me who's interacting with this particular skillet in different random ways. And to some degree, if we were just to label semantics for all of these videos, we might call at least half of them as lifting. But we really know that the interactions are actually different. We are affecting the object in different ways across these different clips. In one, sort of the way I'm holding them or the forces I'm applying to these are really different. And so we wanted to have an approach that, given sort of an interaction clip of a human interacting with an object, could understand that interaction at a physical level. And sort of more concretely, the goal is, given an input video where we are depicting sort of interaction with a known object. And when I say known, it's like we know that it's this precise skillet with this precise 3D model. And we are aware that, and there's some, let's say, even known mass distribution of the skillet, which we assume to be uniform. So given an input video depicting interaction with a known object, we want to be able to infer for each time step what forces were applied to that object and where were they applied at every time step. So of course, this is sort of a very challenging task for which supervision is extremely difficult to come by. And so what we did to address this task is first sort of collect a data set where we took objects from the YCB data set. So these are objects with 3D scans that exist. So we know precisely the structure of each of these objects. And sort of just me and Abhinav interacted with these objects for a few hours, and we collected a data set of interactions with these objects in diverse random ways. But our goal is to be able to infer the physical forces and contact points, right? For each of these objects, what was the force applied at which location at each of the time steps. So one possible way to collect annotation for this would be to just apply many force sensors on each object and somehow get the ground truth data for what forces were being applied to this object at each time step. Unfortunately, that's not really quite practical because force sensors, are not very accurate, and they would change the way you interact with the object because they're not very small as well. So having force sensors would give us very imprecise measurements, and it would make the interactions that we do much more unnatural as well. And so instead of requiring sort of ground truth force supervision, we instead realized that we could just use indirect supervision. So instead, the kind of data annotations that we got on this data set were these key point annotations. So for each object, we manually defined a certain number of key points. So for example, about 9 to 10 key points for the particular drill object that I'm showing here, and got people on Amazon Turk to annotate the key point locations, let's say in every 10th frame of the interaction data set. And what these key point annotations allowed us to do was recover some sort of 3D object pose for each of these time frames. So for every 10th time frame in the interaction video, we have annotations for what the approximate object poses. And in parallel, we also got annotations for where the human fingers are touching this particular object. So for each of the fingers, there's some sort of color code that I'm showing. And we asked people to annotate which pixel the finger is in contact with if they can predict it. And by making an assumption that across the interaction video, the contact points don't change in the object frame, we could actually lift these 2D annotations to 3D key point annotations by just structure from motion. So each of these contact points, we actually could recover in 3D in the object coordinate frame by just assuming that they don't change significantly over the course of the interaction, which may be a limiting assumption. But essentially, we can collect this data set where we have approximate object poses and some sort of contact points for each of the clip. And we can use this for learning. So at a very high level, what we have is, given an input video, we learn sort of two prediction branches. One that predicts the contact points in the frame of the object. So because it's a known object, we just predict the coordinates, 3D coordinates of the contact points, and use sort of the annotations that we have as supervisory signal that the predicted contact point should match the annotated contact points. But sort of more interestingly, what we also predict is a per time step force that is applied at each of these contact points. And as I mentioned earlier, it's extremely difficult to get ground truth supervision for this force. But what we can do is just say that the per time step forces that we predicted, when given as input to a physics simulator, would give us a simulated state for the object at each time step. So given the predicted forces, we have an estimate of how we expect the object to change across time. And we can just say that this expected change or this simulated change that is a result of these forces should be consistent with the image evidence that we have, so that the key points that we expect as a result of our simulation better match the key points that we have annotated in the ground truth. And again, note that this annotation need not be there on a per frame basis. This can be there at a very sparse level, or sort of every 10th frame in our work. And we can still use this framework to learn force prediction without having ground truth supervision. Of course, what this requires is only ground truth labels for these annotated 2D key points, as well as just the ground truth annotated contact points and the ground truth key points, but not really annotation for what precise forces were being applied. And sort of one neat thing I'd just like to note is, when we started the project, we thought being able to do the differentiable physics simulator or set up a differentiable physics simulator that handles these relatively complex meshes would be challenging. But what we realized, we could just do finite differencing with respect to a standard simulator, sort of in this case, PyBullet, and use that as some sort of differentiable physics simulation. And the reason we could do that was that the state space was actually very limited. So the role of the simulator is to take in the current state and the current force and the contact point and predict the next time step. And the state space is actually extremely low dimensional because it's a known object. The state space is simply sort of the rotation, translation, and the corresponding velocities. And so it's a pretty low dimensional system, and given roughly just 20 calls to the Blender simulator, we could compute a gradient for this and actually sidestep the issue for how do we get very good differential simulations for this, which...
one quick question.
Yeah.
So just want to make sure, in this setting, you have the 3D model for these objects, right? Or
yes, so
you have.
So actually not just 3D model. One thing maybe I'd like to note is we have the 3D model, and we also have some assumptions of the density of the 3D model, which actually may be inaccurate, but we have whatever is required to simulate this object.
Okay.
So
okay.
we sort of assume some fixed sort of friction coefficients, some fixed density, etc. I mean, which are still questionable assumptions, but given that, it's still, I'd say, interesting that we can learn some sort of meaningful force prediction.
Okay, thank you.
And I'll just like to show some results.
So Shubham, another question.
Sorry.
So this interest. So another question: when you do the physics simulation, what you mentioned is basically you compute the finite difference.
Yeah.
You compute gradient using the finite difference, but I just wonder how efficient it is to run this in PyBullet. Is it very efficient?
Yeah, it was actually surprisingly fast. As in, I'd go so far as to say that the simulation wasn't really a bottleneck for us.
I see. Okay, thanks.
Maybe that was because we had a machine with a lot of CPUs, but yeah, because it's only 20 calls to the PyBullet simulator for each gradient step that we want, which is not terrible.
Yeah, okay, yeah, thanks.
Yeah. Cool. So yeah, here are maybe just some results where on the left are input videos that we didn't see during training. So these are sort of new interaction sequences of, well, either me or Abhinav interacting. And in the middle, you see the simulated trajectory that we get as a result of the predicted forces. And it's not precise, but it's actually quite accurate. And one thing I'd want to note is we didn't really add any additional priors of what are good forces, and that contact points should not change, that forces at points should not change arbitrarily. So which is why the forces you see on the right are not very smooth, but maybe incorporating certain priors like this would help as well. But we didn't really want to go down that line yet. But still, sort of the simulated trajectories that we see quite accurately match what we see in the video. And one sort of result that was interesting to me specifically was that we could learn contact point prediction using just the annotations that we got from humans, or we could also give the contact point prediction branch gradients through the simulator. So sort of in the column in the middle, the way we get learning signal for contact points is only through the manual annotations. And on the right, the way we get supervision for contact points or gradients for contact point prediction is both through the sort of physical simulation branch as well as the manual annotation. And using contact points in the simulator actually significantly improve the quality of the key points. And here I'm just showing sort of some visualizations, but in the paper we also have some more quantitative evaluation of this. So being able to simulate through the predictions improve allowed not just force prediction, but also improve the fidelity of where we are holding the object, because maybe we needed to hold it in a plausible way so that some forces could be applied to the object. And sort of, if there are any more questions, I'd be happy to take on this or sort of move on.
So I just want to confirm. So for now, your physical inference is single frame based, right? Is there any temporal smoothness?
So it's actually an RNN. So the input is a video, and then we make, I didn't really go into the details of the network, but it takes in a video and infers a per time step forces by looking at the whole video.
I see.
Okay, so I have maybe like 8 minutes. I'll maybe skip a lot of the details in the next one. So what I talked about so far was so what I talked about so far is how we could use the laws of physics explicitly. So we were predicting these forces that were applied to the object, and we hard-coded the equations of physics in the simulator itself to be able to learn this prediction. Sometimes that's slightly difficult to do. For example, if the objects are unknown, we can't exactly simulate them precisely. And so instead of sort of using these explicit laws of physics, we could learn implicit physics models that sort of make the prediction of what will happen as a result of our actions in maybe slightly more general scenarios where, let's say, the object is not known precisely. And these sort of models can let us still learn prediction from images while also, in some sense, learning the effect of the actions with some parameters, as opposed to requiring that everything be known. And I'll maybe skip a lot of the details here, but we just looked at this task, looked at this idea in this very simple setting where we want to plan for long horizon tasks. So there are just some blocks that are present in an image, and we want to take a sequence of actions such that the configuration changes to something desirable. And sort of each action is very restricted, that we are only allowed to push objects. So in this particular case, we should be able to push the blue object around the red one without actually disturbing it. So we need to realize that if we just naively move the blue block to the left, then it will sort of hit the red one and lead to something that's undesirable. So what we really need to do is move it around and not just sort of push it to the left. And so it's really important in this case to have some mental model of how the world is and how the world will change as I act in it. And I will maybe skip most of the details and just note the fact that, we need a forward model. So if we have some forward models shown as sort of purple lines here, that given the current state of the world can predict the effect of actions in it, then we can just use this forward model with classical tools like model predictive control to sort of plan for a long-term action sequence. And so in this work, the focus was on how we can learn a good forward model for this particular scenario. And I will unfortunately not have time to go over a lot of the related work, except to maybe just highlight one thing, which is that the forward model could actually also be learned from random interaction. So given a lot of blocks on the table, we just let the robot sort of interact with these blocks for 2 days, randomly push them around. And this sort of naturally led to many interesting scenarios where things are near each other, pushing one block will push the other block and so on. But just randomly interacting for a couple of days allowed us to get a lot of interesting data. And then we could just learn this forward model in a very simple way that given the current image and an image that I know is a result of my action, I just want a forward model whose effects can explain the resulting image. So sort of given the current image and my known action at time t, I want my forward model, and I'm sort of skipping all of the details here, to give me back an image that is accurate and is representative of what I actually observed to happen. So just using these random interactions in a self-supervised way, that here is my current image, my forward model should be consistent with the image that I eventually see as a result of this action, allows us to learn this sort of predictor P in some way. And I will skip a lot of the details, but maybe also just note that here also we don't need supervision for every particular time step, but we could just recurrently apply this model and only have supervision that is, let's say, k frames apart. So given a current image and an image that is a result of a sequence of k actions as opposed to a single action, also allows us to learn, and that is actually nicer to prevent drift. So sort of at a high level, we take random action sequences and just supervise the forward model to make meaningful predictions that are consistent with the resulting image of this action sequence.
Hello, I have one question. I'm Shangli.
Yeah, sure. Yeah.
So since the action are random, is that possible to find the shortest path from one observation to another observation? Or you don't care about the shortest path, just from this state to the next state?
So we're just learning a forward model, right? So it's more like, here were the 5 actions that I took, and the result of this action sequence, the predicted result should match the actual result. And it's fine if the action sequence I took was suboptimal. So we are not really, so the forward model just needs to predict the result of each action one at a time. It's only when we are searching later through this model predictive control framework that we care about optimality. The forward model itself doesn't care about whether the actions are optimal or not, if that makes sense.
Yeah, I see. Yeah, thanks.
Yeah, and again, I'll just maybe highlight one result here, that for this particular case, when we compare our approach to some prior pixel-based forward modeling work, we see that it could actually make the blue block go around the red block. And at the end, you see some more random actions because it sort of thinks it has achieved the goal. So it's trying to take an action that has no effect. But you can see that the forward model we learned allowed us to sort of plan in this way. And I will skip some more results again. But again, just taking a step back, I showed all of these 3 results, which, in some sense are tackling very different problems, sort of from reconstruction to making a robot interact with sort of blocks on a table. But I'd really like to highlight that all of these essentially are the exact same learning mechanism, that given an input image, we are predicting some sort of models about the physical world and saying that they should be consistent. Sort of the predictions that we get out from this model should really match some sensor observations, and incorporating sort of laws of physics that connect the model to predictions really allows us to learn and bypass the need of supervision. And one last point I'd like to mention in a minute is I really motivated this as trying to do perception that is useful for interaction. So having these sort of world models can allow us to act better. But sort of the way we were interacting to learn these world models was sort of random. And there's sort of an orthogonal question of how is it that we should act to get better sensor input to then learn better world models. And sort of one very popular answer in literature is to take actions that just maximize a prediction error, that make the world models be as wrong as possible, and sort of take actions that are in this way maximally informative. And in some recent works, we've argued that that notion is maybe a bit sort of too restrictive, or it's extremely difficult to learn good world models. So you'll always find interesting actions, you'll always find actions that give you high prediction error. So we've looked at a couple of different ways of defining interesting actions. For example, if you have 2 hands, then take actions where the effect of the sequence of actions is different from sort of doing the actions together. Or for example, if we have access to multiple modalities, then really prefer actions that lead to novel multimodal associations, that if you see an image and a sound that you've never seen the combination of, then that is something interesting to do. But yeah, with that, I'd like to conclude and be happy to take any more questions if you have.
Any questions?
So I have a maybe high-level question. So I think this is very nice talk. So I think in the first part you show some maybe nice results, like reconstructing the 3D shape of maybe animals from like a single image. I think one claim you mentioned in the talk is that you want to make sure that the maybe the reconstructed 3D shape are useful for vision or useful for robotics application. I just wonder, do you have any like high-level ideas like how can we make sure that these like 3D animals are useful for robotics application? Yeah, because I think for 3D shaped objects, I think it's straightforward. We can this can be useful for navigation and manipulation tasks, but for animals, because they are like actually agents, I just wonder, do you have any thoughts? Thanks.
Yeah, no. So I think that's a great point. I don't have a direct answer for how precisely the animals that we were reconstructing are useful, but in my mind, the sort of goal there was to get a method that can let us reconstruct maybe sort of all kind of object categories. So what we started with was, we should be able to really reconstruct any category in ImageNet. And sort of the animals, and actually we also show some more rigid categories there, were just sort of examples that this approach can handle general categories. Yeah, we don't really have robots that right now go out in the wild and interact with animals, but maybe just to construct a use case, if there's figuring out whether the lion is running towards you or not. And so we were also learning pose inference in that case, for example, would be pretty useful. But maybe just taking a step back, I think the aim of the project really is to enable reconstruction across generic categories. And that I definitely think will be useful, especially if you look at a few more indoor categories.
Yeah, thanks. Thanks, yeah.
I guess I have one also a bit kind of high level question. It's like, I think Shubham, you're mentioning that you are arguing that it's important to do perception for interaction, right? Not just perception only. But it seems like currently the work that you presented, a lot of them you define the world model manually. For instance, you define that you want to know the speed or whatever. So have you tried like trying to hook the whole system, like end to end, and then using the downstream task to supervise and see if there's any difference on the world model? Yeah.
So that is something I sort of constantly keep sort of thinking about and going back and forth on, because in some sense, the end-to-end thing that you mentioned is actually the way, if we have a lot of interaction data for one specific task to do. So for example, if you look at any deep RL paper, then that is precisely how they do it, that both perception and interaction are learned end-to-end without any meaningful modularity. But I don't necessarily think that approach is very scalable, or if we want systems that can do a broad set of tasks, then that is the way to go. So to me, actually, it's extremely important that when we are thinking of perception, we put in the right kind of biases that, we understand that the interaction will happen with the physical world. So the role of perception to some degree is to represent the physical reality. And sort of that has been one of the guiding principles for the kind of things we pursue. And I think you're right that if there's a specific task for which we can interact sort of infinitely, then we might not need this separation. But at least my intuition is that if we want to tackle many different tasks, or a common system that can tackle many different tasks, then I think this demarcation would be useful.
Okay, thank you. Does anyone has more questions? Okay, then thanks Shubham again. Yeah, thank you so much for giving such an interesting talk.
Thanks, yeah, it was great.
Yeah, let me give you a clap on the Zoom.
Thank you.
Thank you so much.